from RPS to apparent fluid velocity. Obtaining the fluid velocity from raw spinner measurements and cable speed is a key step in production log interpretation. This is achieved through a process called spinner calibration. This video will show the typical workflow to go from RPS data to apparent fluid velocity using Emerald. The tool string run for this survey contains two spinner types, a full bore and an inline. Typically, two spinners are run in tandem for redundancy. In this example, both spinners are used for demonstration purposes. However, the inline shows considerable noise. In the density track, observe the presence of water in the sump, condensate, and finally a mixture of oil and gas above. The spinners behave differently when immersed in these different fluids. In order to calibrate the spinner, create a new interpretation. Both spinners will be used for calibration. Before progressing to the calibration cross plot, an interval must be defined where the spinner RPS and cable speed will be read. This is done interactively using the spinner calibration zone definition. The number of zones will depend on the number of fluids or fluid mixtures present in the well. In this case, the temperature is used to identify the three different fluid types in the well, and a calibration zone is defined for each. The calibration zones, displayed in yellow, can be modified in size or position by click and drag. They may be deleted by a right-click. The zones displayed in orange are called transition zones, and this will be explained later. Now open the spinner calibration window. A cross plot of RPS on the vertical axis and cable speed on the horizontal is displayed. For each zone, the average of the RPS measurements and cable speed are plotted. The triangles point up or down depending on the direction of the pass, and their color coding is the same as displayed for the passes. The active calibration zone is shown in red on the calibration window, and it is possible to toggle between them using the arrows. The active zone is shaded in the Z track. Clicking on the drop list next to mnemonics, see the spinner selected for calibration. Select the inline spinner or ILS. The cross plot now shows the RPS data for this spinner. Checking the All Points box helps to understand the distribution of the RPS and cable speed data, and how this can affect the calibration parameters. Click again in Mnemonics and select List. It is possible to show both spinners for the active calibration zone. Click on Calibration Mode. 3 modes are available, depending on how the threshold is going to be defined for each calibration zone. Details of each method can be found in the Emerald Help. In this case, since there are 3 very different fluids, use Mode 3 with independent threshold definition for each zone. Select the bottom calibration zone and zoom in on the points. Emerald has already fit a line through the positive and negative points, which maximizes the R-square values of the regression. Using the All Points option, see that some passes show a large spread of data. These will be removed from the calibration lines. By unchecking the Use for Regression box, the lines are automatically recomputed. The slope is one of the calibration parameters that needs to be defined and represents the sensitivity of the spinner. The other parameter is the threshold velocity, which represents the maximum relative velocity for the spinner to start to rotate. By default, these are equal to 0, and a warning message indicates that no correction for threshold is being applied. Click on Threshold. The value can be entered in various ways. For this zone, as it is a no-flow region, it is safe to assume that the intercepts of the lines to the horizontal axis corresponds to the threshold velocities. Click on Copy. The value of the positive threshold is now equal to the value of the positive intercept. Do the same for the negative threshold. Note that positive and negative slopes and thresholds do not have to be symmetrical. Activate the middle zone by clicking on it, and see that it is possible to modify the regression parameters simply by clicking on them and manually applying a value. This zone is still a no-flow zone, and for obtaining the threshold a different method will be applied that splits the distance between the positive and negative intercepts into two equal parts. Now move to the upper calibration zone. Apart from the options seen so far, it is possible to set the slopes of all zones to an average value, although this will not be done in this case. For the threshold of this zone, since this is a flowing region, a value needs to be defined manually as given either by the tool manufacturer, information obtained during the shut-in survey, or the rule of thumb. Finally, a summary of the calibration parameters for both spinners can be found in All Results. Values can be modified from this window. When clicking OK on the calibration window, Emerald will automatically launch the apparent velocity generation window. The option for keeping the apparent velocity for each pass is checked. A cutoff value can be set in order to avoid using very low RPS values where the spinner does not follow a straight line as modeled by the calibration parameters. In this case, Emerald will not be using any value between negative 0.5 and 0.5 RPS. The weight assigned to each pass controls how much the pass will be used for obtaining the average velocity. Click OK. Since we are only going to work with the full-bore spinner, click on Cancel when Emerald prompts the creation of the apparent velocity based on the ILS. Two new tracks are created: VACFB showing the apparent velocity generated for each pass, and Velocity Match, consisting of the weighted average of the velocities shown in the track on the left. The calibration parameters defined for each calibration zone are by default linearly interpolated between zones. This may not be an appropriate approach for cases like this, where the calibration parameters should be constant through the same fluid. The orange zones represent the spinner calibration application zones. In the Transitions tab, the options for defining the range of application of the different spinner calibration zones can be seen. As mentioned, the default is a linear interpolation. If a step-like transition between fluids exists, then a sharp transition at a certain depth can be set. Here, this will be done interactively. Extend the top zone in order to cover the light fluid as seen in the density. The calibration parameters will be constant along the orange zones, and between them Emerald will interpolate the slope and thresholds. Now generate the apparent velocity for CFB only. The calculated tracks are modified to account for the transitions between zones, and this can be seen in the calibration window. In the browser, it can be seen that the curve displayed in the velocity match track is an input of the interpretation. This will be overwritten every time the V-app generation is launched. Expanding the calculated log data node, the V-app generated for each pass is stored. This concludes this video on spinner calibration in Emerald.